Hi. If you have not downloaded the application yet, watch the installation video. If you did not know the general information about the usage of Magic, please watch the walkthrough video. And if you want to learn about speech analysis module, you can watch the speech analysis video. In this video, I will talk about area of interest analysis module. Suppose that you have a video recording of an experiment and you want to identify gaze contact or gaze aversion and their location. If it was a 10-minute recording by a 60 Hz eye tracker, it means that researcher needs to annotate 36,000 image frames. Assuming 1 second for annotating a single frame, for 36,000 image frames, the duration would sum up to 10 hours for the 10-minute recording. Magic significantly reduces the amount of time spent on image annotation. It takes approximately 5 to 10 minutes, depends on the video length. Also, the annotation of faces enables researchers to obtain further information that may not be extracted manually. For instance, OpenFace, which is an open source facial behavior analysis toolkit. We utilized it in the Magic application. It detects the coordinates of 68 facial landmarks. Let me show you those landmarks. As you can see, it draws the boundaries of face with these 68 facial landmarks. Magic also divides the face area into 3 regions. As you can see in this figure in different colors. Blue represents the eye region, yellow represents the nose region, and green represents the mouth region. Magic automatically assigns the corresponding face region label to the raw gaze data. Let's return back to the application. Area of interest analysis module consists of 3 main steps, namely face tracking, area of interest analysis, and review outcomes. At the first step, the face tracking panel involves 2 sub-panels, face tracking with default detector and face tracking with trained detector. We will start with the first one. As you can see, there are 2 fields that expect entrance from the user. The first one is output folder, in which the output files that we will select will be saved under. Let's select the output folder for area of interest analysis. I will use this folder and the video file. You can download this video file by using the links provided in the walkthrough page. As you can see here, I will return back to the function. Since I have already downloaded the video file, I will select it from here. A video belongs to an interviewer, and you have an option to visualize detected faces during the tracking. The output file options are estimated pose file, action units, 3D and 3D landmarks file. These 3 output files are optional. On the other hand, 2D landmarks file and image size file are created by default. Image size file gives the size of an image that OpenFace framework work on it. It's necessary because it can be different than the eye tracker generated image size. Thus, raw gaze data coordinates might be in different dimensions comparing to 2D landmarks. Magic makes a conversion to overcome this problem. In this demo, I will select all the output files. Of course, you don't have to. And then click the track button. It will open Windows. And this will continue until the end of the video. In this part, we are trying to make adjustments before the experiment. Of course, you don't have to use this data. I will show how can you skip this part in the later analysis. So don't worry about this now. As you can see, when it detects the face, draw the facial landmarks, eye boundaries, and pose estimation. Since this is just a demo video, I won't wait until the end of the face tracking. I will stop it here, and I want to show the generated output files to you. As you can see, we selected 5 output files and it generated these output files. This is the 2D landmarks files. When you open it, the first row, the first line represents the headers of the columns, X and Y coordinates for 68 facial landmarks, and before that, frame number, timestamp, confidence interval. It will be between 0 and 1, and the success ratio 0. It can be either 0 or 1, and the XY coordinates. Similarly, you can look at all of the generated output files. If you realize that even though we selected 5 output files, in the output folder we have one more output file. I want to show its content. This is the detected faces file. It's generated to hold the detected faces rectangle. As I said before, to the landmarks file give us this 68 facial landmarks. But if you want to make analysis by supposing the face as a rectangle region, you might need the coordinates of this rectangle. In the detected faces file, we stored this information. This is the frame number, this is the X coordinate, Y coordinate, and width and the height of the rectangle that covers the detected face. And lastly, I also want to show the content of width and height file. It's just 2 lines, and as you can see, the dimension of the image is written under this file, and it can be different than the size of an image that the eye tracker generated. So it's important, as I said before. This is the end of the face tracking with default detector panel. Now we can move to the second sub-panel, namely face tracking with trained detector. In face tracking, some technical challenges might decrease the success ratio of face detection, such as the location of light source. For instance, if the light source is behind the participants, the face detection performance will be negatively affected. Magic enables user to review ratio of the efficiency of face detection. I will also perform those functions in this video later. Suppose that you review the outcomes and you are not satisfied with the efficiency of face tracking. This time you can perform face tracking with trained detector function. By using this function, you will design a custom face detector, and then you will use this face detector to track the face. The training panel is composed of 3 stages: exporting frames, training, and tracking. In the first subpanel, namely the export from the video file will be extracted. Let's try it. We have to select an output folder. I will use this path. Make new folder maybe. Might be a good idea. Extracted frames. Okay, and I selected the video file which I want to make a new face detector on it, and then we will click the export button. It's I think it's enough to show with output files, so I will stop it. Of course, you have to wait until it finishes. It won't take so long. It depends on the length of the video, but you have to be sure that you have enough space before start extraction. Let's open the output folder to see the extracted frames. So far it extracted 843 images. And if you realize that extracted images are stored in a folder in a sequential order. Now let's go back to the application. And also the training sub-panel turns into an editable mode. The image names are displayed as a list on both the select images for training and select images for testing lists. You have to decide the images that will be used to train custom detector by selecting items under training image list. And also you have to decide the test images that will be used for testing the created detector by selecting items under the test image list. It is reasonable to select images on which it's hard to decide image boundary, face boundary in the image, like the ones in which participants walk forward or turned his head, etc. As a sample, let's select 6 images for training. I will start from the end of the list. 2, 3, 4, 5, and 6, and just 3 images for testing. And we have to specify the output folder. I want to make an input folder. Okay. Then we will click the train button. Since there is a validation mechanism in Magic, it warns us about the folder. It says that to select an output folder because even though we rename the new folder, okay, I will use this one, and I also want to delete it, and I will use this one. Okay. And click the train button. Firstly, we are expected to label the face region in each image that are selected for training. You have to press the Shift key and the left mouse key at the same time. Here, this is the first one, second one. Talk one. Done. This will be the last. Okay, after we finish it, you can review the drawings we have just made. and we have to save it, and you can close it. It will automatically start training. Now custom detector is being created, and it will show us the performance of the created detector by testing the detected performance on the image that we select for testing. If you in this image, you can hit enter to process next image. Okay, as you can see, the image is changed, and again hit enter to process next image. Since we select just 3 images for testing, test process is also finished. I want to show you the output folder again. We choose this path as an output folder. As you can see, it creates some files. This is the generated face detector. These are the images that we select for testing, and these are the images for select for training, and also it created an example files for test and training images. When we draw the boundaries of the face, we actually specify the coordinates of a face. In this example file, it holds the coordinates of these spots that we draw on a face. The last stage of face tracking with trained detector is tracking subpanel. It's very similar to the face tracking. This panel performs very similar function with the face tracking with default detector. This time, Magic automatically uses the face detector that we have trained just before. We have to specify the output folder again. I'm not here. Okay, and I will again select visualize during tracking and all of the output files and click the track button. The similar windows are opened, and it shows us the faces selected in this region. I will stop it here again. Of course, you have to wait until the end of the processing. I want to show you the output files again. As I said before, it's very similar with the face tracking with default detector, and it generates the output files with the same name. So this is the end of the first face tracking panel. Now we can move to the second panel, which is area of interest analysis. This panel involves 2 subpanels, namely preprocessed gaze data and faces area of offers an option to fill the missing data in a raw data file generated by an eye tracker. The missing data are mostly caused by billings or temporary problems in eye tracker recording process. The filling function fills the data gaps with linear interpolation. Of course, if you want, you can skip this function. It's optional. But for this demo, of course, I will run it. Firstly, we have to select an output file. Create an output file, sorry. I'll select the path of it. It will get with raw gaze data name assigned automatically. And I will select raw gaze data file. I've already downloaded this file from the link provided in the author page. You can do the same thing as that. Come to the function and selecting already download file. Resources, this one. For this demo, we are using the data taken from Tobii Eye Tracker, but of course you don't have to use Tobii because Magic is Eye Tracker independent. The only thing that you need to be careful about is the file format of raw gaze data file. I want to show format of it. It should be, if you use different eye tracker, the raw gaze data file that you have to select for this step have to be in this file format. First column represents the frame number. The second column should be either fixation or unclassified. As I said before, there might be problems, technical problems in eye tracker, or sometimes when the participant wearing the glasses blinks his or her eyes, eye tracker can't detect the gaze data of participants. On such cases, it will generate data with an unclassified label, and there won't be any coordinates. The third and fourth columns represents the x and y coordinates, and as you can see, all columns separated with space. And the last field that's necessary to perform the preprocessed gaze data function is max gap length. It's recommended that you take this value from the specifications or manuals of the eye tracker device that you employ in your experiments. For this demo, I will use sample data offered in the walkthrough page. It is 2, and then I will click the fill button. It works immediately and give us a feedback about the number of filter of gaze data, in this case 146, and number of total frames, and also give the ratio of filled gaze data. In this case it is 2.50%. Okay, I want to also show you the difference. This is the eye tracker generated data, and I also want to open the output file and compare the results. The output path is demo, and this one is the gap field data. This is the eye tracker generated data. For instance, in the 35th row line, as you can see, it is represented as unclassified, but in the gap filled one, this line interpolated with the previous and the later eye trackers coordinates, gaze coordinates. So if you want, you can use gate-filled raw gaze data, pre-processed gaze data to increase the available raw gaze data amount. The second subpanel is faces area of interest. It can be used to define the boundary of the face and then to test the conversation partner's gaze direction. Magic automatically annotates each image frame to identify whether a participant is looking at the interlocutor's face or away from it. And also it holds the relative positions of gaze data to the face location. I want to show you a figure to make it more clear. As can be seen in this image, the image frames are theoretically divided into 9 regions, 3 rows and 3 columns. If the gaze location is outside the face boundary, one of 8 characters, namely A, B, C, D, F, G, H, I, letters is assigned as an area of interest label to represent that an interlocutor is looking outside the participant's face. If the gaze of the participant is inside the interlocutor's face, then E letter is assigned to as an area of interest label to represent the in situation. Moreover, if the participant is looking at the interlocutor's face, the face area is divided into 3 regions, as I said before, and eyes, nose, and mouth, and a corresponding one of these 3 regions is also stored. Let's run the function. We have to create an output file again. I will select this path. Okay, the faces region of interest file name is automatically assigned. And then we have to select the raw gaze data file. If you fill the raw gaze data by using the pre-processing gaze data, you should select this field file. So I will select it. As a 2D landmark file, you should select the 2D landmark file that's generated during the face tracking process. I'll use this one, and image size file that's also generated when we run face tracking process. I will again select this one, and the image size in this pilot study, the image size that's used for inside the Tobii eye tracker is 640 and 380. And fixation error, it's an optional choice. you don't have to enter value. You can leave it empty. But I recommend you to use enter value to handle drift errors, which are the systematic errors of the eye trackers. This is specific to eye tracker, and in this case I will enter the value for specific to Tobii glasses. It was 4.84 and 5.34. You can find these values by looking at your eye tracking device specifications or manuals. And then I will click the Analyze button. It immediately finishes, and I want to show you the generated output file. This file is generated. When you look at this file, you will probably realize that these huge numbers. I intentionally generate this problem to show you the fixation of it. It's about the regional setting of a decimal separator. In an application, we specified 2D landmark files, and in the 2D landmark file I want to show it. That is used as a decimal separator. If your separator is different than this, it might be a comma, for instance. In this case, it works wrong. So you have to change the decimal separator. I'm using Windows 10 and I'm showing the appropriate settings for Windows 10. If you are using different operating system, you have to search and make similar settings for your computer. As you can see, decimal symbol is selected as comma, or however I want to use that, and digit grouping symbol as a digit grouping symbol I can use comma. I will click apply and OK buttons, apply and OK buttons. Close this, and I'll delete the generated file. Unfortunately, we have to rerun, restart the application and rerun the same function. To make things faster, I will copy the selected input text and then use them when I restart the application. This values. Last one. Now I'm closing the application and I will open it by typing its name. Then I will navigate to the related function and copy the input text. To the landmarks file, this is the image size file, and then image size 640 and 400. button. This is the generated output file. As you can see, this time reasonable values are presented. First column represents the frame number. Second column represents the area of interest label, and the comma separated for coordinates represents the face that is covering the rectangle that's covering the face. This is the x coordinate, this is y coordinate, and this is width, and this is the height of an face rectangle. And this is the eye tracker raw gaze data. This information is generated for all of the frames, and also you can see in some cases there are some other informations. As I showed before, if the area of interest label is E, which means interlocutor looking at the participant's face, we also assign one of three face region, according to the gaze data coordinates. In this case, it was eye rectangle, eye region, and also again we append the face rectangle coordinates. If we we don't have an gaze raw data, we couldn't decide whether participants looking at interlocutor face. So in such cases, we use specific labels. If gaze raw data is absent, we use gaze raw data empty. If there is a problem during face detection, we assign this label. And if there is both face gaze raw data empty situation, and also we couldn't detect the face, we use both face detection and gaze raw data empty label. This is the end of the face as area of interest subpanel function. Now we can move on to the third step, which is review outcomes. This step provides the user the opportunity to review the outcomes, and the review outcomes panel is composed of the following subpanels: visualize tracking, find area of interest detection ratio, label area of interest manual, and lastly reanalyze area of interest considering manually labeled area of interest. The first panel is visualize tracking subpanel. The interface enables the user to display the video file overlaid by facial landmarks, area of interest label, and gaze point location. It provides an option to the user for specifying and correcting systematic drift errors, and it also gives an option to specify a confidence threshold for facial landmark accuracy, and an option to visualize just experimental interval. Let's try the function by entering the required fields. I'll select the video file, this one, to the landmark file, and here raw gaze data file. I will choose the field raw gaze data file, area of interest file that was generated just in the for the second step. It was this file, image size. I enter the size of an image generated by eye tracker and confidence threshold. I will enter Toby glasses. Sorry, confidence threshold, not for confidence threshold, for fixation. I will enter this value and I want to leave empty confidence threshold. As I showed you before, into the landmark file, there is a specific column representing the confidence level. It's between 0 and 1. You can type the threshold if you want. I want to visualize all of the frames, that's why I will leave it empty. Visualize just experimental interval, it's optional, but I highly recommend you to this option because it doesn't meaningful to visualize the recording before the experiment or after the experiment, so I leave it as checked. And experiment interval file, this file is generated in the speech while we are performing functions under the speech analysis. If you if you didn't run the speech analysis functions, you should watch the related video and run it first. I will select it. Experiment interval file as an eye tracker frequency. I will enter 30 Hz, and this is a pair record. This is the first participant's interviewer's recording, so I will choose the first participant, and the eye participants is 1. This values, as I said before, is about the is the same with the values that we have already entered in the under the functions in speech analysis module. Then I will click the visualize button. As you can see, it draws the facial landmarks. This is the frame number. It's presented at the top left corner in a red color. Right below it, there's a confidence interval of the detected facial landmarks. This value is between, as I said before, 0 and 1. And pink dots represent facial landmarks. And also you should realize that there is a green rectangle, and there is an yellow dot inside this green rectangle. The yellow dot represents raw gaze data, and outer green rectangle is drawn by adding fixation errors on the raw gaze data. This is the visualization of face tracking data. I will stop it. And we can move on to the second step. Find area of interest detection ratio. You might think that visualization give information, general information about our success ratio of face tracking, but you probably need some statistical values. By using find area of interest detection ratio function, you will get such information. So in this function, firstly we have to enter area of interest file. Choose this one, and then experiment interval file. It is this one, and then I trigger frequency, and then the first participants, and the ID is 1. Then click the find button. It immediately finishes and give us a feedback. I intentionally use this video recording to show you how reviewing outcomes might be important. As you can see here, approximately 60% of area of interest were not detected. This is not an acceptable value. So in such cases, you might wonder about the underlying reason. Visualize tracking by displaying video file overlaid by facial landmarks, area of interest labels, and gaze point location. You will get an information. In this pilot study, we realized that interviewer was looking from an outside the glasses while looking at notebook to read questions or to evaluate the interviewer's responses. So to increase the ratio of labels, area of interest labels, you can use custom detector by using the face tracking with trained detector subpanel and repeat the remaining area of interest analysis functions, and or you can label area of interest manually. This brings us to the third subpanel, which is label area of interest manual. The input fields of label area of interest manual is very similar with the visualized tracking. So I will enter them as quick as possible, create an output file, I'll select this pet, this is the assigned name, as a video file, I'll select this file as a 2D landmark file, I will select this one as a raw gaze data file, I will select the one that is filled the gap inside it, more field as an area of interest file, I will select this one as an image site. This is optional, by the way, you don't have to enter it. Enter the values. Again, I will leave this when the confidence threshold empty, and I will enter the fixation values, and I will leave it checked as an experiment interval. I will select this file, the frequency of eye tracker, the first participants, and this participant ID, and then I will click the label. It opens a window, and in the left corner the frame number is written, and right below it there's a confidence threshold of the detected facial landmarks. If you think you can assign one of these labels by looking just at this image, you can use the number pet to assign one of these area of interest labels. These are the letters. If you click 7, it will label this frame as A, and if you click 8, it will label this frame as B. And if you want to skip this frame without labeling, you can click the enter button. So let's try it. Open this and okay. Done on this one. I'll click. By the way, if you don't have number pad in your computer, you can of course use the numbers at the top of your keyboard. The next frame will be opened immediately after you labeled the existing frame. You can skip by this way. I am some random values. You can go back to the previous frames by using keys. This function generated file at the end of the video recording. Label process is finished. Now I want to show you the corrected frames output. It includes just two columns. The first one is the frame number that we have assigned new area of interest label, and this is the letter representing the area of interest area. So we can move on to the last step, reanalyze area of interest considering manually labeled area of interest. This panel provides a function for merging automatically extracted and manually labeled area of interest. Manual labels override the existing automatic labels. I want to show perform this function also as an output file. I'll select this pad, it assign this name as an output file. This is the area of interest file. This is the raw gaze data file with the fit one. This is the landmark file. This is the image source file inside of an image of an attribute, and click the Analyze button. Function completed this job, and we can now look at the output file. The name of the output file is faces. This file is a generated output file. This is generated file. When you look at it carefully, you can realize that it's in the same format with a file that's generated automatically and named as faces region of interests. So I guess this is the end of the area of interest analysis. Please feel free to contact us if you have encountered any problems.